Thank you all, quality engineering community, for coming. Thank you, Vitali, absolute hero in life. This is a talk on digital twins, model-based V iteration. So this sounds like something ChatGPT invented, but it's not, trust me. And before I continue with this talk, I just want to say a little disclaimer on AI. So I know there's a talk on LLMs coming up afterwards. I want to say there's minimal AI use in this talk. There's no AI slop. Hold on, it's just human slop generated by me, right? So just bear that in mind. If something goes wrong, just blame me, right? Okay, all right. So I hope this is the abstract that attracted you here. You're not just here for the free pizza and beer. You want to learn a little bit about digital twins, and that's what I'm about to talk about. So this is a very much an introductory talk, because I've spoken with a few people here, and we come from very different worlds. I'll tell you a little bit about my background in a bit. But most of you guys are QAs, right? Or from the software testing industry, so forth. Okay, and that's why this is a real back to basics beginner talk on digital twins. And I know digital twins was a buzzword many years ago, but it has real world uses. So I'm going to talk about what they are, how they work, and why they are transforming industries and the testing process. And that's the heart of this talk, the what, how, and why. And we're going to sort of cover that in the reverse order in this talk. So we're going to start with the why. That's the first section. So you can have a big picture orientation, the context, and so forth. And then we're going to talk about how. So digital twins is just a fancy word for models and simulators and interfaces and so forth. And then we're going to ground that into the what, the actual examples used in automotive testing, aerospace testing, medical devices, and so forth. And if that sounds like too much, please feel free to ask questions throughout. Let's make this a little bit more interactive and discussion-oriented. Happy with that. Okay, so why, how, what, ha. Let's start with who. All right, who am I? There's my mugshot. My background is I'm a physicist to physician by training. So I've been around various areas of science, engineering, medicine, and I've worked in scientific software development, scientific instruments, which is where I currently work. A little bit about me as just a little bit of trivia. I'm a native Londoner, but that's not internationally enough for me. I've spent time living in like 6, 7 different countries. And one of the things you do when you live in different countries is you learn about languages, right? You're communicating with people, you're learning about the different ideas. And that's sort of what this talk is, because we're talking about human languages, technical languages, business languages. That's sort of where digital twins comes into it. So now I want to learn a little bit about you. Hands up, who here has heard the term digital twins before this talk, before the abstract was shown? Hands up. How many? Oh, it's very few people. Cool. Okay. If the camera didn't catch that, there's a room of about like maybe 40, 50 people here, and like 5 people raised their hands. So, okay, it's very, very much a beginner talk. Okay, the context, the why. What's going on in the world right now? Can someone tell me some of the big trends that are happening? Anyone? AI? Yeah.
There's a boost in the digital world, which is changing rapidly.
Rapid digital changes, yes.
Plus, it's more harder for the ones who are more lazy.
Yeah, correct. Humans are lazy, okay. No judgment.
Is it a trend?
Yeah.
Well, really not. Digital twins reminds me of metaverse.
Yeah, okay. Yeah. Quantum computing, yeah. All the fancy physics happening.
Coin is growing.
Bitcoin is growing. Okay, Bitcoin is growing. All right, so if you want to talk about trends, the best way to talk about trends is through memes, all right? Memes are trending. So the way I see it, and you may disagree slightly, but there are 3 big movements, big paradigm shifts occurring throughout the world. The first one, electrification. So, the push towards renewables, solar power, wind power, tidal energy, so forth, means we've got to reimagine traditional devices. And now these new modern devices have more and more electronic components in them. More electronic components, more hardware, computational hardware, more compute power, more software. The second thing, and this you sort of touched on with AI, and there's a reason I didn't put AI here. I just want to broadly categorize this as automation, because automation occurs at the software level, at the hardware level, and there's robots, both software robots and hardware robots, which are transforming industries and transforming traditional manual processes. And then you have digitalization, and you might think, okay, these are all overlapping. Yes, it's not exactly a one-to-one, three different paradigms, but digitalization, just moving data onto more digital formats, going away from the old ways of doing things. So what are the consequences of these things? Software abundance, proliferation. Now this makes software sound a bit like a weapon, but it's not, because what we have is just more lines of code and more things to test. So this is why all of your jobs, I hope, are secure, because everything is being run by software at the moment. If we go by industries, so here's our six little diagrams here. Let's just go through one by one. The first one, electrical cars or electric cars. Can anyone tell me where you would find software in an electric car?
So, sir, driving,
Yeah.
automated driving or whatever.
Yes, automated driving systems. ECUs, electronic control units, yes.
Zero vision, driving.
Yes, driving systems, ADAS, yes. Batteries, that's a big one. Modern day battery technology. What about aircraft? Drones, unmanned aerial vehicles, yes.
Flight controller, yeah.
Flight controllers, yes. Autopilot, yes, in actual piloted flights, yes. What about industrial automation and machinery?
Agriculture as well.
Agriculture?
Agriculture is being automated.
Yes, agriculture, agrotech.
Assembly lines.
Yeah, assembly lines. So you have programming logic controllers.
And medtech laboratories for sequencing genes and all this other role.
Yes. Biotech, pharmatech is also a lot of automation happening in the process management there. What about renewables? Solar technology, wind technology, where do you find software?
Grid control.
Hmm?
The grid control.
Grid control systems, yes. The power distribution units.
I guess there are also microcontrollers that manipulate how these solar panels move, for example.
Yeah.
As the wind.
Exactly. So you want the solar panels to orient themselves depending on where the sun is positioned throughout the day. So you have controllers for that as well. Yeah. This one's a bit abstract, but what I really meant is city infrastructure. So just look at this room. There's like lighting systems, ventilation systems, heating, fire alarms, and so forth. These are all areas where you would find software. And then the last example, medical technology. So you have now software which is used by doctors, by nurses, by practitioners, and also software which is used by patients. So patient monitoring devices and so forth. So this is what you would call software-defined plants. And there's controllers in them, embedded controllers, which manipulate and, essentially, they're deep-rooted within these plants, and they're essentially a fundamental part of this. And so the question is, more software, more electronics, that's a good thing, right? That's a great thing, because things never go wrong when you put more electronics together, right? Okay, this is just a little bit of a funny example because it's got a panini mode. But here's a touch screen toaster that I saw on Amazon. And one of the reviews, the touch screen is great, but the toasting is not. Okay? So the team that was responsible for developing the touch screen, they got it bang on. The toasting people, not so much. And it's funny to read this because, okay, this is funny, but if you go to your car and the infotainment works, so that's a touchscreen, but the brake system doesn't work, that's a problem, right? Right? So that's really is now the motivation. How would you be able to test more and more sophisticated software-defined plants, and essentially go through the development process that you guys do with traditional software? So, who's seen the V diagram before?
More hands up.
Everyone's hands up, right? We all love the V diagram, okay? It's beautiful. I mean, it evokes bad emotions, but it's beautiful in some sense, right? Because you start at the very high level requirements, and ideally this is the point where people should come together and discuss what they want and clearly express their intent and so forth. And then you dive into the details, you go into the implementation, and then you come back up, you get your units ready, you move to components and systems and integration and so forth. And this is nice. This is very, very nice because it allows multiple stakeholders to get involved in the decision making, and multiple stakeholders are also responsible for assuring the quality, to ensure it's a high quality software product. But this becomes difficult to do when your software is going to live in a car, or it's going to live in a plane, or it's going to live in a medical device, because you as software developers or quality testers, you may not have access to that actual car. That's the challenge. That's really is the problem. And the thing that most of the QA community, you've already sort of solved this problem with test-driven development, all right? So it's a philosophy, but the idea is good. You define your tests first, and your tests are based on requirements, and people have understood the requirements, so your tests are really driving the quality of your software. And you bake into it test automation, CI/CD workflows, and so you can continuously evolve and iterate your software. But without having your actual plant, your actual car, your actual surgical robot, your actual aircraft, it's impossible. How do you do this? How do you do this?
Simulate.
Sorry?
Simulators.
Simulators.
Yeah. That help
Yeah.
to integrate the system for having an actual results of the machine which have physical appearance.
Okay, so you should be giving this talk, right?
Trust me,
You should be giving this talk.
today is your day.
Yeah, exactly. Ah. Okay, all right. And the idea of V-iteration is, what you want to do is you don't want to just go following this path. You want to swiftly and continuously iterate between these different stages as needed. And for that, a virtual copy of your physical plant is what will enable that. And that's what we call the digital twin. Does anyone have any questions at this point? Have I motivated this enough? All right, cool. So, digital twins. They are twins of the digital variety. If you ask ChatGPT, it will basically say, it's a dynamic virtual model, mirrors a physical system in real time for analysis, simulation, optimization. It's clear, right? That solves everything. You don't need to go any further. No. So, okay, digital twins was a bit of a marketing jargon a few years ago. People used things like cyber-physical assets and virtual replicas and so forth. But in practice, when it comes to cars, batteries, planes, trains, devices, whatever you name it, these are mathematical models that represent the behavior, properties, so forth of your physical system. These models are placed on specialized simulators, and these simulators are equipped with interfaces that interact with the real world, the real devices that are under test, right? So let's break that down bit by bit. So first things, the models. What are the models? So models are multi-domain digital assets in themselves. They're usually developed by a combination of regulators, domain experts, and in-house teams that deal with software development and testing. you're trying to measure the behavior properties, data of the actual system. You need to account for physics, chemistry, biology where it's necessary. Your real system might have mechanical, fluidic, electrical components. You need to integrate that into your model in an effective way to ensure that it realistically represents the system, realistically as much as it's needed. You know, when people think of model, they think of like a 3D visualization or 2D visualization like that. And that's part of it, but the model isn't really just human facing. It has to be facing your device is under test. The device, the control software that is being tested must think it is connected to the real car, not some digital twin of the car. It is connected to the digital twin, but it must believe that it's in the real car. And that's what you want to simulate, right? So you can go through desired fidelity. You can do really high fidelity models. Flight simulators, for example, may have real physics in them. Or you can do low fidelity models. You know, your braking system, your controller might just need to check that the brake pedal has been pressed. That's all you're simulating, the pressing of the pedal, not more, right? And it depends. It depends what you want to do. But really, you want to build up a sophisticated and, you know, realistic model that will allow you to then deploy onto a specialized simulator. So here's an example of one of these specialized target machines. So this is a microgrid test bed. So it's a digital twin of a microgrid. So electrical grids used in power systems. We'll talk a little bit about this in a bit. And this company builds these real-time operating system, offline capable entities. And these are massive cabinet-sized structures. They have power supplies, signal conditioners, other fancy electronics that allow you to basically, you know, create that realistic interface between your model, which might live on a desktop computer, and your devices under test. It'll definitely be equipped with interfaces. So you'll have your analog, digital, sensor data, so temperature, audio, visual, you name it. You'll be able to build that in. Those like specialized electronics there as well. Who's heard of communication buses like the CAN bus? Yeah, most people. Yeah. So CAN bus, Modbus, Ethernet. You know, every industry has its own communication protocol. So these will also be pumped into this. Now, this piece of electronic, this simulator, you know, you can buy a very simple simulator and it might punch out low voltage signals. So, you know, you might be okay for testing, but you might want to test real power grids, like real scenarios. So you can connect this up to a power amplifier and you can go up to megawatts, so forth. And you can really test things like fault cases, electrical failures and blackouts and whatnot. So you can go one step further. And so combining your models and your simulators, you can build an end-to-end infrastructure. You have a block modeling environment. You go from your requirements to your model. And then from your models, you can automatically generate the embedded code in C, C++, VHDL, whatever you want. That will live on your embedded, you know, on your embedded devices, or on the embedded system on your simulator, and then you've got your digital twin. And so now with this workflow, you can go from requirements to testing. You can start automating. Requirements-based test automation using digital twins. That is the key. That is the key. So,
Mitesh.
yes.
So we've been using simulation for testing all the time,
Yes.
mocks and so on. And like, where does that layer of simulation, which most developers take for granted, end, and where does digital twins begin?
Yeah, this is a very good point. And I do want to answer this towards the end. But if I give you a rough answer, is I would say with digital twins, at least in the context that I'm talking about, so specific industries, automotive, aerospace, medical devices, industrial machinery and automation, there's usually domain experts that are involved in the conception of these models. And there are regulatory requirements for the quality of these models. So I will say a little bit towards the end, but you hear digital twins also in the context of business. So like virtual customers, and you can do test campaigns, and you have someone simulating a customer group and you're doing some marketing analysis with that. That's okay, but there's no regulators involved, right? And your data might be based on a few questionnaires, and you might have built up a model of a customer. Whereas this would involve real physics, real chemistry, real biology, right? And you need to take that into account. And there are approved frameworks which you follow to develop the kind of models that you need. Because at the end of the day, this software is going to be living in a performance or safety critical environment. So your models need to have the right level of fidelity. It's not guesswork models. It's years and years, decades of science that is built into the digital twins.
I have a very, very simple example. So when I'm building my microcontrollers, and if I run my tests on my machine, they run with the speed of my machine. When I run them on the microcontroller, they are much slower. So if I had a good simulator of that microcontroller, then its speed would be limited to what the microcontroller has, and my tests would be much more relevant to the platform.
Yes, there's the whole real-time element of this as well. So a lot of these simulators are real-time. They run a real-time operating system. So you have those processing capabilities that are needed to mimic real-world scenarios, at least at the signal and power levels. Okay. So models, simulators, that's our digital twin, right? That's our digital twins. And normally when you do your controllers under test, you hook it up to the actual plant, but now you can hook it up to your digital twin, which simulates or emulates your plant. And you basically get the same feedback loop, and you can do the same software quality testing. What is the benefit of this? Well, this is the term that I call model-based V-iteration. So let's break that down bit by bit. It's model-based. So now you are independent of the actual plant. This model, virtual asset, digital asset, you can move it around between teams, right? No one owns it. It's not like a car. You have to move from laboratory to laboratory. You have a virtual asset that everyone can tap into at the same time and do the necessary tests that they need, right? Infinite reusability. Okay, infinite is kind of the wrong word, because you just saw that simulator that's also going to take a lot of energy to run. But in principle, you can reuse models throughout the entire development process, right from your early requirements down to implementation, back to unit component system integration testing, so forth. All right. And the best thing about models is, what did I say about language? About communicating with people from different backgrounds, right? That's essentially what happens when you're developing a car or a plane or medical device, whatever. You're communicating with different stakeholders: government, healthcare, engineers, specialists, whatever you name it. And models is a way of translating requirements into
Layman.
Yeah, well, layman, yes, but it's a way of translating requirements into a usable format by multiple entities.
So in other hand, how you are giving the commands from the layman to the computational powers
Sorry?
or source to use 10 commands from the layman to the computational power to the simulator to get data. So it's like sending for example, I don't have experience working with the simulators, but I still remember like 10 or 10 years ago, I had kind of event. They mentioned the simulator for the APS braking system for us.
Yes.
So now I remember it, but I'm very curious to know. As a regular QA, we write our test cases, the scenarios. After that, we switch to the automation part, having multiple scripts in different languages. But for the model, how it works.
Well, the model is in its own, you wouldn't say it's a programming language, it's just a block modeling environment. Maybe if you've heard of tools which allow you to basically create composite models, they look like flowcharts. They embed the necessary equations and so forth into it. You can use your programming language like C++, Python, whatever you want. But the idea is the models themselves, they exist at a higher level. They exist at a closer level to requirements. The requirements are written in human language, right? So the requirements are written in human language, and you have different bodies which are needed. So in-house in a company, you might have domain experts, you might have modeling experts, you'll have engineers, you have QA, and they will all read the requirements and interpret them quite differently. But with models, it's built by the domain experts and the regulators. Now it's tightly bounded, right? It's tightly bounded. The equations or physics or whatever you're trying to model is tightly bounded. And you can use those models themselves to automatically generate the code that you need.
And every time we need assistance as a human to transfer the model data into the layman language to make the decisions.
Ah, okay. So this is about certification artifacts. So this is also, now this is now a new industrial movement. And sorry for going a little bit off topic, but the idea is you can generate all certification artifacts. And that's actually one of the things that I want to talk about. So the models bind together the requirements, codes, test cases, everything together, and certification artifacts such as documentation that you would need to prove that the controller is doing what it's supposed to be doing in accordance with the standards or whatever body you're regulating with. And so that also is now automated. So it gets rid of the human writing part of it, right? So there are, the models themselves are responsible for managing that translation, right? And, we got to think about digital twins very carefully because they are a part of the testing workflow. They cannot be the entire thing. At the end of the day, you still have to test the software in a real car, right? There's no getting around that. There's no getting around it. So the models basically just help facilitate parts of the development process. And that's the important thing to remember. There will still be the automotive regulatory standards are massive, right? The control software part of it is very small, right? But even then, it's quite challenging to do without this type of infrastructure. Yeah? Did that answer your question?
Yeah, I got it.
Good. So that's the thing about digital twins, right? So like I said, they allow you to trace your certification artifacts to codes, models, and so forth. And then you have all the things that you guys have done very well. So all the test-driven development infrastructure with test automation, CI/CD, pipelines, it's all there. It's all available because now you just hook into your digital asset, your digital twin of your physical plant, and you can basically carry out the exact same tests. And so you guys as QAs, you can just hook into the digital twin. You can run the exact same test cases. Maybe Qase will have that implementation in the near future, right?
Well, we did think about getting a mobile lab, and that would be best done if we had proper simulators of mobile phone, which is still non-existent.
Okay.
iOS simulator is not what it should be.
Right, okay. Very soon though.
Well,
So we've done the why, we've done the how of digital twins. Let me show you some actual examples, which is, I hope, why you're here. So the first thing, vehicular hardware in the loop. Hands up, who's heard of the term hardware in the loop before? Okay, very, very few people.
Now,
Now you've learned it.
no idea here.
Okay, so the idea of hardware in the loop simulation, so it's called hardware in the loop simulation or hardware in the loop testing, is really just about testing with digital twins. So you have a simulated or emulated physical asset, and that replaces your actual physical asset in the control loop. And so the hardware in the loop simulation basically allows you to test, in this context, parts of cars or vehicles, so cars, aircraft, ships, whatever you name it, either the entire vehicle or subsystems of it. And you can pick and choose depending on what kind of model you've built. And ideally, if you work in a good company, build a modular model so you can pick and choose the relevant parts to your development. Now, this is a video. I'm not sure if I can show it. Nah, we don't have time for that. But I'll share the slides later. You can have a look for it. But this is a nice hill simulator setup. So you've actually got a 3D simulation. You've got the control system, and you've got, you can see the actual controller here in use. And then this guy is operating a crane on the sea. So you can basically see all the software elements of this are being tested. And then here's your hardware in the loop simulator. Okay, and this is really ideal for things like off-road vehicles like tractors, because they often enter riskier environments, not just on the road. So you can really simulate farm conditions or agricultural environments, rough weather scenarios, and so forth. You test the electronic control units, as you mentioned. There are other ones, flight control computers, FADEX for traditional aircraft, programming logical controllers, which is what you see here in this video. This is now not just the hardware in the loop, but it's actually got a human in the loop, because the human is moving things around. So you actually can do operator in the loop feedback. So mechanics, designers, early stage testers, they can get involved very, very quickly, at the beginning of the development process, to make sure that the system is working as intended, right? So you don't have to wait until the actual tractor is ready. You have now, operator in loop feedback. Test your software way, way earlier. I just mentioned a few certification standards here, but so the next example, this is also a video, but we're not going to cover it. Emulated batteries and grids. So the next evolution beyond just hardware in the loop simulation is power hardware in the loop emulation. And so emulation basically goes beyond simulation by introducing real voltages, real power signals. So you're amplifying the voltages produced by your simulator to get realistic scenarios. And this is great for testing power electronic components and batteries and so forth. So modern day batteries, advanced batteries are very complicated with battery management systems. They vary, batteries, they age, they degrade, there's heating effects and so forth. You can put all of that into a model, and you can test algorithms like state of charge, state of health. And your digital twin of the battery, you can age it. You can move it to its end of life, or you can make it brand new, or put it in dangerous scenarios like overheating, overcurrent, overvoltage. And you can really cover all of those edge cases very, very safely.
So when you're building a camera, for example, you can then simulate what's going to happen when the battery is overheated.
Yeah.
It's how your camera behaves in this scenario.
Exactly, yeah. So you can cover all the dangerous and risky scenarios without actually damaging your real hardware. So that's question.
I was just wondering, if one is developing against a digital twin, and if the digital twin does not is not as real.
Okay. Yes, it's not good fidelities. Yes.
Fidelity is not there at the granular level. If there's a small deviation, couldn't that affect the implementation, thinking that it's working well, but then on the real thing, the edge case would not see it because the simulation was not the same as the real thing?
And this is again why you have domain experts and regulators involved in the development of the models, because part of the models is also to understand the limitations of them, right? All models, is as I learned at university, garbage in equals garbage out, right? That's the definition of models. And models they rely on human interpretation. Human scientists are humans, engineers are humans. They rely on the interpretation of physical phenomena. So the models have limitations. And the other thing about testing, especially edge cases, is you build in tolerances into your testing, right? So you account for that in your test cases for extreme scenarios.
There's also cost of quality as well. So you build higher fidelity models when the cost of quality is higher.
Yes. Yeah. So what Vitaly said is actually a very good point. For companies that are seriously invested in digital twin workflows, there is a high upfront cost to making an exceptional quality, exceptional fidelity, representation of their physical asset. And companies do this because at the end of the day, once you have the model, that's your grounding truth for at least a decade. You go from batteries to power electronics that run our grids, relays, converters, inverters, you name it. And in this case, you can actually simulate very, very rare events like blackouts due to extreme weather. So there's no point waiting around outside for a rainstorm, right? You can just simulate it. Simulate what will happen and test the blackout, test the robustness of your system against the potential hazardous scenario. I do want to, one other thing is just pre-commissioning. Digital twins, they're not just at the early stage of the development. More and more industries, more and more applications now use digital twins as a route towards commissioning. So you ease your software and control systems into the real world scenario by slowly replacing bits of the digital twin with the real physical system. Step by step, you integrate into your real product or end technology.
I would like to add to these reasons of simulation, like celebrating a day of our planet, because I know for an energy industry it is awful day because people try to save up our planet and at the same time switch off all the devices with candles, and after that at the same time to switch on all electronic
Yeah. So you can, you can plan around festivities as well, of course. Good. The last interesting example. This is the one that, brings me the most joy because I've been involved in this sort of area for a while. Virtual patients, digital twins of human physiology, digital twins of organs. So Siemens Healthineers, they're doing, cool things with this sort of area. You have the actual biology, chemistry of humans, and you can use it to test medical devices like MRI machines and so forth. You can really validate the software that exists in some of these more sophisticated medical devices. And this is, again, one of those things that is now, not endorsed, but it's now becoming frequently mentioned in new certification standards. And if anyone knows anything about med tech, certification is the end goal for most of the companies. And digital twins of patients, I hope not many of you want to be test cases for the first surgical robot, right? Better it's done on a virtual copy of you. So that's what this is. So I hope I've covered most of those cases. I'm going to just wrap up and let's go through. So digital twins, models and simulators, I hope we are all happy with that, is basically a bounty of testing. You have a digital copy of your physical asset. You can run all the test cases that you want. I hope that makes all the testers in this room very happy, right? I hope so. And the iteration, you can go back and forth along the V diagram as needed. Okay. The last thing is I just want to throw out a few ideas, business ideas for some of you entrepreneurial people in there. Can we go from those models and simulators into a more standardized format? So this is one thing, something that is far closer aligned with certification standards. Can you go beyond just ordering simulators and building models in-house to, having off-the-shelf, customized, plug-and-play devices that will allow you to build digital twins in real time cheaply and efficiently? And speaking of cheap, instead of buying all of this hardware, let's leverage that thing. What's that thing called? Cloud, right? Digital twins as a service. So if you can have a virtual car living somewhere far away and any developer can develop, can test their control software, brake system, whatever they want against a virtual replica, all the right interfaces and whatnot, ship it off, you get a test report back with all your certification artifacts. That would be the gold standard.
All the thing if it has one.
Yeah. And with that, thank you very, very much. Thank you, Vitali. Absolute hero. Thank you, Qase. Thank you, JetBrains. Few companies, my digital twin is there. Cheers.
Thank you so much.
Any final questions?
Were there any cases when the digital twin had the issue, despite of all the certifications and the regulators, and it was found out while testing in real life with a real machine?
Are you asking if there are like, are there like bad digital twins? Is that what you say? Yes, of course. Of course, there must be.
Maybe one story.
I don't know if I have like the legal liability to talk about these sorts of things, but I mean, in vague terms, there's like digital twins of an aircraft, I know. So that this aircraft didn't actually exist, but it was a figment of engineers' imagination, and they made a digital twin of the non-physically existent aircraft. And they've done all the controller validation and that sort of stuff. And of course, when they went to the regulators, they still wanted to see the physical thing, but it doesn't exist. So I'm stretching the truth a little bit here because I can't talk about it, but if you meet me afterwards, I might share something with you over drinks. Good question.
Myself asking you the names of one of the good quality simulators tools, because in the end we have a human life on the risk, especially for the ICU devices
Yes.
or any simulator or physical hardware, because in that case on the digital side we can lose money, but where we have an actual real human.
Okay.
Can you find some of the good quality simulators tool and why that tool? Because I knew some of the tools and each tool have its own quality.
Now, I can't promote any companies in this particular talk, but talk with me afterwards. I think the beer might give you some answers. Yeah.
You can lose.
Because I played around with many, so I'll be able to tell you a few, depending on the context. Yeah.
What is the price of such tweet models? Well, let's say we wanted to develop some program for a car, and we need to build a model as a car to make the product for it.
That seems it could cost much more than the handle solution.
Yeah, you know the cost is. This was like a sort of a promotional talk on digital twins, but haven't talked anything about the negatives. And there is a high upfront cost, right? It's not just money. You need to now pool resources in your team to develop the model rather than developing the actual product, right? But for some companies, this is a better investment to make because this model that they will develop, this digital twin, is something that they can use for 10, 15, 20 years. A good example I can give you is a tractor company that I know, and they've developed a fully modular model of their tractor, right? And their company actually sells, 50 different kinds of tractors. So they have a really modular model of a tractor, and you can plug and play, and you can, emulate the different kinds of tractors that they are selling. And also it's flexible enough so you can extend it. So when they have new additions to their tractors, you can incorporate that into their digital twin. So that is an investment they made up front. And, maybe the traditional V&V process for tractor ECU validation is maybe 2 years, right? They've spent 2 years building the model, but the validation process is now 3 months. And the next time they have to do it, it will be 3 months again. That's the benefit of this sort of framework. It's not saying there aren't cons to digital twins. There are. For companies, this is expensive. This is why one of the things, as a business idea, if you're interested, if you can invent something which is off-the-shelf digital twins or digital twins as a service, you offer it very cheaply, anyone can do it.
Or democratize the way of building them. You
Yeah.
better be the service as well.
Democratize education. That's what this is about. Yeah. Because a lot of models and things are proprietary, right? So you have to be a domain expert or something like that to be able to interpret, read the papers and so forth. So democratize, as Vitali said, the process of building models. So, more people have a chance of developing high quality software. This is community science, but in digital twins.
Thank you.
Yes.
Someone actually talked about the fidelity, right? So I'm just curious if, like, for example, if we look at, let's say, the fidelity required for digital twin of an airplane versus this tractor. Now, they might be the same, right? We might require the same fidelity, or we might not. But is there any emerging standards in terms of how people are expressing this fidelity in terms of the digital twins that they're developing?
Yes, the specifically to the aircraft, there are regulatory bodies like the Federal Aviation Association in the US. You have also the equivalent here in Europe, and their certification standards now explicitly mention things like hardware in the loop testing, and they also set out guidelines guidelines for developing models, or the kind of models that are trusted in the industry. So these things are circulated, they're still proprietary, but there are frameworks existing and being developed to ensure the models reach the sufficient the desired level of fidelity to pass their certification standards. Yeah. Okay, thank you very much.